I'm the senior project scientist for the James Webb Space Telescope.
Okay, I'm Zhang Hu from National Astronomical Observatories. I'm project scientist of the optical facility of the Chinese Space Station telescope.
Hello everyone, I'm Daf Dan from Tencent Games.
This is Zhou Zezhen from China, studying at Shaoxing No. 1 Middle School, also a normal astronomy amateur. I'm truly honored to take part in Tencent WE Summit.
I'm Gou Lijun, the professor from the National Astronomical Observatories here in Beijing, China. And I'm the moderator for this activity. This is 2022 Tencent Science WE Summit, a deep space exploration dialogue.
Okay, James Webb Space Telescope is 6.5 meter diameter telescope to study infrared light from the distant universe. It is observing everything from the first stars and galaxies and black holes to planets in the solar system.
The CSST is a 2-meter aperture wide-field space telescope to be launched into the same low Earth orbit as that of the space station. CST will have a comparable angular resolution as that of the Hubble Space Telescope, but with a very large field of view for its camera. I believe that camera will be the largest one in space for astronomy at that time.
Thanks to the CAS program led by the Institute of High Energy Physicals, I have a chance to really involve in this area. Initiated by the Institute of High Energy Physicals, the CATCH program will launch more than 100 X-ray satellite telescopes to capture space phenomena. Tencent Games started to engage in this program last year. What we do is to try to apply our technologies in AI for game to help the satellite estimate space environment and carry out observations in an intelligent, coordinative manner. Thanks.
JWST is undoubtedly a very challenging project. Could you tell us about major challenges it faced and share with us some lessons learned from the project?
Yes, well, the telescope engineering is extremely ambitious, and we needed to develop 10 new technologies, including how to focus the telescope after launch, how to make the telescope out of 18 smaller hexagons, because we could not launch a single mirror as large as we needed. We needed new kinds of infrared detectors, which were actually similar to previous ones, but had to be performed much better. We needed a refrigerator, a device to cool one of the instruments down to a temperature of 7 Kelvin. We needed to prove that we could unfold that gigantic sunshade and have it work in outer space, which is actually quite difficult. So
I believe so.
it was actually quite challenging for us. We had to design it and build it and test it, and then it did not work. Design it again, build it and test it again, it does not work. But finally, after 4 tests, it works. So we are so pleased that it did, because there's so many ways for something that large and complicated to fail.
Thank you very much.
All right.
AI 在很多的这个应用里面都很成功所以呢就是想问一下，就是在什么应用场景下面效果比较好那么它的局限性是什么？
就是 AI 目前就是说，可能确实由于这几年深度学习和生物强化学习的一个发展，能够帮助我们在很多领域里面都解决了以前没有解决的一些问题，或者是达到了以前解决问题中达到不了的一些效果。但是呢，本质上来说，目前的 AI 的核心的算法还是基于整个统计和统计推断相关的一些理论的，所以呢，它会有比较 也会有非常多的一些局限性吧。首先，第一个，它的这个训练成本和部署可能需要比较高的一些成本。然后第二个呢，就是说，因为所有的这个解决问题的方案和经验都是从历史的经验、数据或者是生成的数据中这个自我产生的数据中所学习出来的，所以它相对来说比较难以处理一些从未见过的一些场景，对。然后第三个来说的话，就是，它的可解释性比较差，所以我们通常在做真正的 AI 的一个实用性的时候，会要做大量的测试，确保它是 stable 是稳定的，然后，并且能够这个很好的适应这个我们所解决的这个问题。Hello, Mr. Mather. My first question is, are there any significant discoveries already or latest findings?
The new discoveries. Well, okay, we can say a few things about what we've already observed. We have observed planets in the solar system. From Mars and Jupiter and Uranus. We observed a collision of the probe that was sent out to collide with an asteroid that was done with the DART mission. We've observed planets around other stars already. We are able to tell that some planets have water vapor in their atmosphere, although those planets are much larger and hotter than the Earth. So we're not ready to say that there's a planet like Earth out there. We've observed black holes. As you know, most galaxies have black holes in the center, and one of them is pretty close by, and we managed to obtain information about the things that are orbiting around near it. We are observing star-forming regions. A beautiful area we call the Carina Nebula is home of thousands and thousands of new stars being born inside their dust clouds. So the telescope enables us to see through the dust a little bit and see the stars being born with planets. We've even seen a few places where new stars are being born in their little dusty disks, and they're seen in silhouette against the glowing background. So we're beginning to learn about all of the things astronomers wanted to know, and we've even had already a surprise. It seems that the first galaxies and black holes grew very much more quickly than astronomers had predicted. So we're seeing evidence of that, and we are anticipating some big surprises.
Yeah, doesn't matter. As a normal astronomy amateur, we are always interested in small bodies in extreme conditions like black holes and something unknown like dark matters and dark energies. So how does JWST study black holes, dark matters, and dark energies?
Okay, well, of course, dark matter and dark energy are transparent, so they're really invisible. We can only detect their effects. So our first public image we released shows a cluster of galaxies that is so massive that the light going through that cluster is focused and bent and by the gravity, so we can measure the presence of the dark matter by the presence of its gravity. And so we use it as a tool so that we can see more distant galaxies. Of course, everyone wants to know what are you going to discover? And of course, as an astronomer, you never know what you are going to discover. But what are the most important targets that you plan to point the telescope at? What is the plan for the first observations?
Right. So CSST is mainly a survey telescope, but of course we want to get science results out as early as possible. We have discussed a bit about early science observations, but we have not determined which objects to be observed yet. However, there are some ideas. For example, some nearby galaxies like F31. It will be a very beautiful galaxy, a large galaxy. You cannot image with Hubble entirely, right? But we have large field of view. We can do that with multiple bands from near UV to near infrared. That would be an amazing picture. We possibly would observe certain globular clusters as well, some nearby dwarf galaxies. I think just like JWST has done, we certainly would like to use galaxy clusters to study strong lensing effects and so on. We plan to get more solid, say, early science observations next year.
张辉老师，就是，我就有一个问题啊，就是现在我们在地面上，就是全球各地，就是都有很多的大量的一些大面积的巡天望远镜，全球各地都是非常多的，而且他们很多都是有像主动光学啊、自适应光学的这种东西。这些望远镜，说实话，他们的这个分辨能力啊，还有这个视野啊，都已经是相比于那种空间望远镜差距也不是特别特别大了。而且我们现在地面望远镜我们可以做的很大，就像比如说我们甚至未来各国的那个 TMT 的那些项目，30米的，也没有说航天运输的这种限制，因为航天运输它也是有这个运量的一个限制。那这样子看的话，那计划内大概口径2米的这个 CSST 有什么特别的一个优势呢？
非常好的问题啊，看你对这个天文也是非常的熟悉。那么我先说这个，就刚你关注的这个自适应光学。那么自适应光学的话呢，它的这个观测的市场呢是非常小。它虽然能够矫正这个大气的影响，获得接近于这个衍射极限的这个分辨率，所以实际上巡天和这种精细观测呢是相辅相成的。那么在天文上面，经常可以看到的很好的例子，就是大的巡天呢找到非常有意思的目标然后呢精测的望远镜呢再去跟踪观测，把它这个很精细的研究。那么巡天呢又通过这个再深的巡天呢去把这个天体的这种统计属性能够在这个研究的更清楚更好。那么再说地基的巡天望远镜的话，它受大气的影响，它观测的波段首先是受限的，它是在这个主要是可见光波段，但是它紫外就观测不了。那么我们 CSST 的话，紫外的这一部分，近紫外这一部分是非常有特色的，而且呢，在今后的大概十几年内，那空间的话呢，也没有这样的高分辨率的紫外这个观测的望远镜。第二个来说呢，就是刚才说巡天望远镜市场很大，它就没法用这个自适应光学，所以它的分辨率就会差那么这个空间的这个2米望远镜的分辨率，那就又能做巡天，又分辨率很高，所以这是它的一个很大的优势。
明白，谢谢。
我们 CSST 的话呢，做那个巡天编排，那么有点像旅行商的这个问题那么它要便利好多地方那么需要是以最小的代价去完成，而且受到很多的约束那么这样的一个问题呢，刚才说了，就是说如果没有个训练集的话，好像是这个 AI 用起来就可能比较困难，是吧？
类似于像这个旅行商问题的话，实际上我们认为这样的问题是类似于我们叫做这个组合优化问题它本身有自己的很多确定性的解法，它本身也是个 NP 问题。如果是像用在巡天这样的场景里面，当然还会有很多各种各样的限制存在。就是我们在处理这个问题的时候，是本身把整个卫星配合整个观测天文现象的问题，就是把它建模成一个多智能体协作的一个问题，然后通过这个多智能体的深度强化学习的算法来训练我们这个卫星的这个决策模块，我们可以在反射环境中用计算机模拟来进行大量的这种探索。然后另外呢，会有几十个不同的宇宙空间的这个随机的这种现象的一个模拟，然后去做这种暴力式的一种探索。但是在探索的过程中呢，我们会把这个比较好的一些策略吧，然后用一个神经网络来 进行表述，实际上可以把这个神经网络看成一个函数，对，我们输入当前的一个状态然后就出来一个我们应该是去寻哪一块的天空，或者是应该去进行一个联合的一个跟踪的一个任务，对。当我们真实部署到整个大的环境中的时候，通过这个神经网络就会很快的就可以做决策。
In China, astronomy is developing very fast. For these young people, can you give them some idea of the astronomy research in perhaps the next 10 years?
I think it's a very exciting time to be an astronomer because we have new equipment, and new equipment means new discoveries. From black holes to planets around stars, there's just so much excitement. So, on the other hand, most of us that study astronomy can't always be professional astronomers. So it's a beginning of a scientific career where we go do something else after we learn some astronomy. An astronomer is capable of understanding a wide area of physics and engineering. So it's a good preparation to be a professional in a scientific or technical field, and especially in data analysis. So astronomers learn data analysis almost before anything else. So, by the way, here we're using the language Python for analyzing the Webb telescope data, and that's something that many astronomers will share with many programmers.
Thank you very much.
I have a question about the CATCH project. I'm delighted to hear about it, and it will be very powerful. So I'm interested to hear what do you hope to discover with the CATCH project? It's very different from other kinds of telescopes.
CATCH will launch a fleet of small satellites outfitted with X-ray telescopes, which will work together to carry out round-the-clock, multi-target, multi-parameter, and multi-waveband observations in order to follow and observe multi-space phenomena such as black holes, neutron stars, gamma ray bursts, supernovas, and so on. In addition, with the help of AI technology, every satellite is able to conduct intelligent analysis of what it has observed. If something valuable is observed, it will automatically notify other satellites. Then all the satellites will relay to observe a target around the clock. In this way, we hope to improve the efficiency of observation and have a chance to capture space phenomena never seen before.
大付老师啊，就是这个 Cache 的这个 AI 本来不是一个游戏一个 AI 吗？那目前现在这个 Cache 项目它训练 AI 的这个方式是什么？然后为什么会有一个这样的想法，就是把一个游戏用的一个 AI 用在一个天文的一个项目里面？
这是一个很有意思的一个问题啊，也很有趣。最早强化学习可以归属到这个训练动物的行为这些训练上的，就是说训练者通过动物行为达到他的目标来给予动物一定的奖励。对，强化学习算法原理也跟这个比较类似。那在开始项目中，首先要定义好这个卫星星座这个整个卫星星座的观测收益，这个收益就是根据天球上面这个不同爆发源的观测的时长啊、重要性啊，以及这个相关的其他的一些综合得到的一个观测得分。这样通过不停的这个迭代跟进化的话，这个开启的整个星座观测收益就会得到一个最大化。对，游戏 AI 跟开启项目呢，实际上它背后的数学原理本质上都是比较一致的。对，我们在跟这个中国科学中心的这个教授们一起讨论完了之后，觉得跟我们平时在游戏当中的这个很多场景是非常非常类似的，所以呢，当初就达成了这个合作吧。对。
Actually, how will the data become public so all astronomers can compare your observations with other observations with other telescopes? How do you plan to do that? That's a very important thing for astronomers around the world to be able to compare the different observations.
There are different models. One is like the Vera Rubin Observatory. They would release catalogs, right? And then through collaboration, you can get the raw data and so on. But we do intend to make it as open as possible. And at the same time, its observations are also very complementary with other projects of its time, such as JWST, the Vera Rubin Observatory, the Euclid mission, and the Roman Space Telescope. And I believe these projects together will provide extremely rich data sets for potential breakthroughs in studies from the solar system all the way to the remote universe.
So I hope your project works. We all want it to work.
Thank you.
No matter it's JWST or CSST or CATCH project, all have revealed the scientific spirit of human beings' continuous exploration of the mysterious universe, which is also the driving force to promote the future development and progress of mankind. I hope today's dialogue can bring you some inspirations, and I also hope that more young people who love science will join us in the future to explore more possibilities. Finally, great thanks to our guests for their participation. On the 6th of this coming November, Tencent WE Summit will be held. Professor Mather and Professor Jiang Peng will share more wonderful views about the JWST and the Chinese Fast Telescope, respectively. Welcome to watch our live broadcast. See you then.